Alright, welcome back. In the last video we talked about dispersion forces. We're in section 3 of chapter 11 discussing intermolecular forces. So now what we want to do is turn our attention to the next intermolecular force here in section 3, and that's dipole-dipole forces. So dipole-dipole forces start here on page 490, and essentially they're an intermolecular force that are caused by permanent dipoles in a molecule. And remember, the reason you have a dipole in the first place is because you have a polar covalent bond. So a difference in electronegativities, and then thinking about the three-dimensional structure of the molecule, those polar bonds don't cancel each other out, leaving an overall polar molecule. So if you have a polar molecule like water, and you bring another polar molecule close by, another water molecule, they'll have special interactions. Their dipoles will interact, repel, and attract one another. And that's a second type of intermolecular force. So here is the image. Here we've got two molecules that have dipoles. And notice we're drawing a dotted line to show the intermolecular force between the two molecules. So that dotted line is kind of an image of the intermolecular force, or the interaction between the molecules. Remember, it's not a real bond of any sort. It's just an intermolecular force that we want to sort of visualize. So polar molecules have a permanent dipole. It's because of their shape, and that means they're going to have attractive forces between different other polar molecules, the best way to say that. So if there's a dipole-dipole force, that means there's going to be a larger boiling point, a larger melting point, compared to nonpolar molecules which don't have dipole-dipole forces, especially if they're a similar shape and size. So we're going to compare molecules of a similar shape and size because they have the same molar mass and the same sort of dispersion force, so we can focus on what difference dipole-dipole forces make without thinking about the other types of intermolecular forces at the same time to get an idea of which ones are stronger. So here we have formaldehyde and ethane. And notice the molar mass is virtually the same, so the dispersion force should be virtually the same. Their surface areas are pretty much the same. So the only difference between these two molecules is dipole-dipole force. One's a polar molecule and one's nonpolar. Ethane being nonpolar, formaldehyde being polar. So we predict, seeing these two molecules, that formaldehyde would have a higher boiling point and would have a higher melting point compared to ethane. Now, I can't tell you exactly what that number is, unless I do some experiments or I go and look it up or something else. But I can tell you formaldehyde has a higher boiling point than ethane because it experiences an intermolecular force that ethane doesn't have, namely the dipole-dipole force. And indeed, that's what we see when you look it up. So here we have a situation, excuse me. Oops, going the wrong way there. I didn't mean to put this box in. You can compare different molecules. Let's see if I can get rid of that. Okay, so the higher boiling point belongs to formaldehyde. Now, if we compare different molecules together that have different about the same molar mass, but the difference is in the polarity, in the size of the dipole moment. So notice each of these molecules, we're plotting the dipole moment here, and as the dipole moment gets larger, that means the polarity is stronger and stronger. The boiling point goes up and up and up and up. Notice it's not a huge difference, but it's still a difference. Keeping all the dispersion forces the same, but changing essentially the dipole moment, we see with increasing dipole moment also an increase in boiling point. Okay, so as we've seen here, increase of the dipole moment, larger dipole moment means more intermolecular forces. Let's put that into practice and see if we can work an example problem. Determine if dipole-dipole attractions occur between CH2Cl molecules. Now, how are you going to figure this out? Well, you need to know, is there a dipole moment in this molecule in the first place? And so that means we're going to have to figure out the three-dimensional shape. So we're given what the molecule is, which means we can look up the electronegativity of all the different elements. We can determine if there's polar bonds, and then we need to find out, do those polar bonds cancel, or do they lead to having a dipole moment in the molecule itself? So we want to find out if there's dipole-dipole attractions, and we know that means, is the molecule polar? So from that formula we're given, we'll have to draw the Lewis structure following all those rules. We'll have to figure out the bond polarity and then determine if the molecule itself is polar. So we got to remember those three-dimensional shapes. Or we just got to look them up in the book, right? So here's the Lewis structure, the Lewis dot structure for this molecule. Now remember, that central atom carbon, there are 4 electron regions around that. So that means this molecule is tetrahedral. Tetrahedral meaning a 4-sided figure. And the difference in electronegativities we can find by looking up the electronegativity values of each of those elements. And so we could say that chlorine to carbon bond is 0.5 difference in electronegativity. So therefore it's a polar bond. And there are 2 of those that occur. Do those 2 cancel each other out? And the answer, of course, would be no. It's a tetrahedral shape. This means in that tetrahedral shape that you have an arrow, a dipole moment arrow that points through that carbon atom in the middle in between those 2 chlorines. So you've got the 2 chlorines pointing up and you've got the dipole moment. Let's see if I can do this right. There you go. Dipole moment pointing toward them, meaning the electron density is being pulled further away from the carbon and closer to the chlorines themselves. So remember the crossed arrow, the end that's crossed means it's more positive on the side with the little plus sign, the little cross arrow. Okay, so the negative is pointing toward the tip of the arrow is what I'm saying. This means since there are polar bonds and since that means they don't cancel out in a tetrahedral shape, that we have a polar molecule. If we have a polar molecule, then we can have dipole-dipole attractions or dipole-dipole intermolecular forces. So another related question might be, what are all the intermolecular forces of this molecule CH2Cl2? Well, we could do the same analysis we just did and see that it has dipole-dipole interactions. So that's one intermolecular force. And we know it has electrons, so it has dispersion forces. So that's a second intermolecular force. Choose the substance in each pair with a higher boiling point, so the ones that have a greater intermolecular force. So notice the first one and the second one. Notice we've got these 2 fluorines, one on that side, one on that side. So that means they're pointing in opposite directions, and that means they should cancel out. If there's a dipole moment, they're going to be pointing exactly opposite each other and cancel. On the other one, both of the fluorines are on the one side. Notice there's 4 regions around that carbon on the right. And so those 4 regions make the geometry around this carbon tetrahedral. And so we have the same situation we just looked at in the previous slide. There's a dipole moment pointing toward the fluorines away from the carbon, meaning the electron density is closer to the fluorines. So of these 2 choices, this one would cancel, the one on the left here, and the one on the right would have a dipole-dipole force, which the one on the left doesn't have, so the one on the right should have a higher boiling point because it has more intermolecular forces. Notice the surface area is about the same, and notice the molar mass is the same, so the dispersion force is the same. Okay, how about part B here? We've got cis, which means the chlorines are kind of on the same side, and we have trans, meaning they're across from each other. So which of those 2 would be polar or nonpolar? Okay, notice this one on the right here, the trans, they would cancel each other out, and the one on the left, the cis, they would add together. So we're predicting part A, it's the one on the right, part B, it's the one on the left, and together then those are the ones that have a higher boiling point. And the higher boiling point means there are more intermolecular forces present. Now, we have one more intermolecular force we need to talk about, and this next one is the strongest one, and so we want to make sure that we give a lot of good time to it. So I think we're going to stop the video here, and then we'll move on to hydrogen bonding in the next video.